What I'd like to know is, let's start off, and I would like you to figure out what was the question that we asked in part 1 of the lab, and what was the thing that you had to hold constant. So take a minute, look at part 1. What was the question that you asked, and what did you have to hold constant in order to answer that question? Okay, so let's go. Feel free to raise your hand and give me some info on that. Let's go with the question. Trish.
So the question was, how does the acceleration of a system change based on that force?
Good. So, how does, I'll write A for acceleration depend on F net. Now, I'm going to have you guys write that in your notes. Okay? I know you've got a lab and everything, but I want you to have it in your notes too. So the part 1 question was, how does acceleration depend on F net? By the way, who had an intuition about that? Anybody feel like they knew that beforehand? How do you think acceleration would depend on net force? You made a prediction, after all, a couple days ago. Anyone want to share what they wrote? Do you remember what you wrote? What did you think was going to be the case? How did you think acceleration would depend on net force? Anyway, Anthony.
I thought as net force increases, so will acceleration.
All right. How many other people thought, as net force increases, so should acceleration? Raise your hand if you said something like that in your prediction. Okay, extremely common, right? And that's kind of a common sense thing. The harder you push on something, the more it's going to accelerate. Now, even though you expected that, we're going to really look at it carefully here with data, and we're going to see how does it actually change. So if it increases, fine. Does it increase in a linear way, a non-linear way, etc.? Second thing here, what do we have to hold constant? What do we have to hold constant in this part of the lab? We're changing net force, we're measuring acceleration. Sagar, what do we have to hold constant? The mass. So what we held constant was total mass. And I think in this lab, remember, it's 2 objects that are connected by a string. So that means it's really M1 plus M2. And we had to hold that constant. What was that mass, by the way? How much was it? You might have to look in your notes for this because you may not remember it. How many kilograms are we talking about? 1.2 kilograms. Yeah, I'm going to write that up here. That might be important for us. The fact that we have 1.2 kilograms that we hold constant. Now, one of the things, do you remember, how did you make this experiment happen? How were you able to increase the net force on the system, but not change the overall mass? Because I thought the force was the weight of that fallen object. How could you add weight to that fallen object, but not change the 1.2 kilograms? What clever thing did you do to make sure that you didn't change this? Do you remember? This is a good lab question. What did you do practically during the lab to make sure that you never changed that 1.2 kilograms? It was always the same. So no matter what your F net was, your total mass was always the same. Trish?
You moved the weights from mass 1 onto mass 2.
Exactly. You transferred masses from cart to hanger, cart to hanger. You never took masses out of the system and put them in your pocket. You never stuck stuff on there that wasn't in there in the first place. You only transferred them. So that's really important to remember that. You had to play the game of just moving the masses. All right, cool. So, graphs. I saw everyone had really nice graphs on this, so I'm just going to take the liberty of sketching what I saw that pretty much all of you had. You made a graph of acceleration versus F net. And yes, go ahead and sketch that in your notes. We're not going to put a scale on that or anything. We don't need to. But you tell me, what shape should I sketch in here? What was the shape that you got when you made this graph in part 1? Alicia, what was the shape? Yeah, are you sure about that?
Oh, is that exponential?
Oh my. You guys love exponentials, so you've never seen an exponential that's close, but you like them. No, go ahead. Look at your graph. Look at your graph for part 1. You put your lab notebook away.
Yeah, it was linear.
Yes, okay. Yeah, it is linear. Chris?
Why is it that it wouldn't be a diminishing sort of graph? Because it couldn't go faster than 9.8 meters per second. Really?
I don't know. That's a great question. How come it doesn't accelerate? How come it doesn't go beyond a certain point? Okay, I'm going to leave that for now because we didn't go. The maximum acceleration that you had was not close to 9.8, was it? What was your maximum acceleration? If you look in your data table. What was it? 55.
1.5.
Oh, 1.55, right. So you were well under. You were well under that. Yes. So one possibility here, Chris, is that maybe when you get up to a certain point, you might actually have to apply additional force. If you could push down even harder than the weight of that object, you could keep this going perhaps. But in this experiment, yes, we are probably kind of limited by that. But we didn't even get close to 9.8. That's a good question. But we didn't even approach that because we didn't put that much weight on it. But you are right. I think we would be limited at 9.8. But your data, to address your point, your data really looks linear here, right? It seems to be going up the line. So what does this mean? What type of a proportion do we have between acceleration and net force if you have a linear graph like this? That's a direct proportion, and that is a really important part of this whole thing. I'm going to put a star here and say that acceleration is directly proportional to what? To what? Look at your graph. What is acceleration directly proportional to? Yeah, F net. That's very important conceptually. You can see that from the graph. So what does that mean? What does that mean, like, in terms of numbers? If I doubled my net force, if I were to actually apply twice the force to an object, to a mass, what should happen to its resulting acceleration? It should double, right? If I triple my net force, what should happen to my acceleration? It should triple. And that's what direct proportions are. So basically anything you do to the x, y is going to change by the exact same proportion. And so that appears to be what the data is telling us. Now, math, look at the shape. It's a line, right? A math teacher would say, hey, that's a line. And a math teacher would say that goes along with the formula that y is equal to slope times x plus an intercept, right? In math, you learned about that, like, going back probably to 7th grade. It's the equation of the line. Can we make use of this in a physics class, though, and can we match up some of these things with actual physics quantities? We can. So I don't want to write y and x. This is physics. So what did I actually use for my y? What variable, what quantity was I using for my y? A, acceleration. What quantity was I using for my x? F net. So I'm going to write that down here. Now, my slope, well, I don't know. The slope is just the steepness of the graph. It's some number. I'm just going to still write this as slope. Whatever. It's not clear to me what quantity that is. And how about the intercept? If you look at your graphs, what is the intercept value-ish? 0. So, and that kind of makes sense because if you don't put any force on an object, it's not going to accelerate. So we can ignore this. That apparently there isn't really an intercept there. So my question is what's the slope meaning? Like, what's going on with that? I mean, we've learned that acceleration is proportional to net force, but we don't really know what the slope is. So one of the things I had you do in the analysis was I said, first of all, find the slope. Find it. All right, get the value. Okay? And you had to come up with some kind of number for that, right? Did you guys all do that? All right. So you get some number. And then what did I ask you to do with it? Take a look at the analysis. What did I have you do with the slope of that graph? I didn't just say write it down, you're done, because the number itself probably didn't look very familiar. But what if you take 1 over that slope? You do 1 over the slope. You tell me, I'm going to point to you, and you tell me what number you came up with when you did this on your calculator. You took 1 divided by your slope. All right, Gabby, what'd you get? 1.25. Jagisha, what'd you get?
0.88.
You made a mistake. Chris, what'd you get?
Like 0.56.
Ooh, you made a mistake. Mateusz, 1.2. So remember, Gabby was 1.25, you're at 1.2. Marcin? 1.2. Vincent? 1.27. Okay, Chris, what'd you get? 1.04. It's a little bit low, but in the ballpark. Alicia, what'd you get?
1.27.
1.27. Okay, we're getting a lot of people who are in the range of about 1.2. This is where making a really nice graph, plotting your points carefully, and really drawing a best fit line totally pays off. Because if you do that, you should be getting something really close to 1.2. If you did this well, you should be getting something like that might be off a tiny bit, maybe 1.3 or maybe 1.1 at the low end. But drawing a good best fit line by hand and sloping it should give you something pretty close to this. Why is that number significant here? Does this jump out at you at all? 1.2? Yeah, have we seen that at all? That's actually the mass of the system, right? It's the same number there. And that is not a coincidence. If it is a coincidence, it's a real coincidence. Like, wow, that's really weird. But the fact that the number comes very close to that mass is really telling us something. So I'm going to make a hypothesis here based on this. I'm going to hypothesize that maybe 1 over slope is equal to mass. Right? It seems to be. It seems to be. It seems like if I take the inverse of that slope, I'm getting the mass. If that's true, then the mass should be equal to 1 over the slope. Isn't that how inverses work? You flip one side, you flip the other. So if this is really true, if my hypothesis is true, then, oops, I just wrote the same thing. I wanted to write the slope is equal to 1 over the mass. Yeah, is that right? 1 over slope is equal to mass. Is it also true that slope is equal to 1 over mass? Just kind of cross multiplying? And this is my hypothesis, right? So the reason I'm making this hypothesis is I'm going to come back to this formula, and I want a good physics formula here. I want something that has physics in it, not the word slope. So I think maybe that this formula really should be acceleration is equal to 1 over mass times net force. That's my hypothesis based on this first data set. I'm going to say that this could be true. Right? I'm not totally sure. I need more data. But it looks like the slope has this meaning where the slope is 1 over the mass. Okay. Now we want to test that. We want to see if that's really true. So that's what part 2 is about. In part 2, we're going to deliberately change the mass and see how it affects the acceleration. And maybe we'll get some data that supports this formula. Because if this is a formula in physics, this would be really important if we could link these things up. So I think it is. We're kind of not totally sure yet. We know that this and this are proportional, but is this really true? We've got to find out. Okay? All right. You guys have questions?